David Axelrod is a clinical associate professor at Stanford University School of Medicine and an attending physician in the cardiovascular intensive care unit at LPCH Stanford. He cares for children. Oh, thank you. He cares for children with critical, congenital, and acquired cardiac diseases. And as Walter mentioned, he uses VR in surgical training. And today on this stage, he will demo the Stanford virtual heart as well as other things. Thank you.
All right, well, thank you very much. Thank you, Lisa and Walter and everyone. I'm proud to speak to you here today. This is, I'm a little bit of, I think, a high-maintenance speaker with my own little table and everything, but we'll try and get through it here. VIP, yeah, not quite. As Walter spoke about the uses of VR in healthcare broadly, and Walter is a longtime world's expert on VR. I'm one of the guys he mentioned who thought VR was invented like 4 years ago. And so that's been really fun for me because for my whole career, I've been a clinician. I'm a pediatric cardiologist, so I take care of kids with critical heart disease, most of which are babies that need heart surgery or some procedure immediately after birth, or other children and some adults as well that have either congenital or acquired heart diseases. And I'm going to kind of walk you through a little bit to how we ended up using VR at the Stanford Children's Hospital here in the Heart Center, and then show you an example, and then hopefully leave some time for discussion and questions. I should let you know that the company that builds the VR I work with, the company's named Lighthouse. I'm their lead medical advisor, just in disclosure, so that most of what you'll see today are the projects that we're working on at Lighthouse. So one of the things that's really cool about working in VR in medicine is, anybody who's done any training in medicine or has been part of medical school knows that it's really an art and a science. And so in the course of, developing this VR technology for healthcare, I've been able to speak at a few places that have been able to demonstrate that for me, and I'll show you a few pictures of those. So here I was in the Netherlands this summer, where I saw this, which is a piece of art in the Rijksmuseum, and I looked at it and said, well, that's just like VR. It's like art and science all together for medical VR, and how cool is that? And then when you start thinking about things like, there's a bunch of engineers in the room, right? Fibonacci sequence, right? And so you look at these numbers, and then you find that actually these are all over in art. And so the combination of art and science, I was in Barcelona this summer, and if you look at Gaudi's architecture and art, these scientific concepts are everywhere in art. And so, I set a little bit of a high bar for myself by looking at these, masters in what we wanted to do with our VR in healthcare. But for me, it kind of started this way. Who remembers the Atari in '78? Some of us grew up on this. This was Superman in 1978. I loved it. This one, Pitfall, Asteroids, these were great games. This now has become, at least in the gaming industry, has become things like this. This is now already 3 years old, but this is, Batman. There's probably as much data and information in the tip of Batman's little wing here as there is in the whole game for Atari. And so over the course of time here that Walter's been, working in VR, and, where I was like 5 years old, Walter, we've really gotten so much more technology that we're really able to leverage and use that's gotten us to the point of what I'm going to show you, much of what we're talking about today. So my field, this is what I do, every day in my clinical job at Stanford. I take care of children that have congenital heart disease. Just to give you a quick primer, it's the most common birth defect in humans. It involves frequently abnormal formation of the embryonic heart. So when the heart's forming is in fetal life, it's a very complex folding structure of the way that the heart forms. Which means that there are really countless variations. So it's very routine for us to be sitting in a conference with surgeons and physicians with combined 500 years experience, and we show the images of a heart, and people in the room will say, we've never seen that. We have no idea what the development of the embryology was for that because it's so complicated. And because of that, it's really difficult to understand and to picture and to get a three-dimensional image in your head of what this heart is actually, how the blood is being pumped in this heart based on two-dimensional scans. And so we actually ask a lot of our trainees and our physicians and also of our families to take those two-dimensional images, put them together and construct them in their head and get a three-dimensional image of what's going on in the heart. And in order to do the job that I do and that our trainees do, you have to have that picture pretty clear or else, patients can suffer. So I'm going to just kind of give you a brief look into the journey for how this came about at Lighthouse and at Stanford. We are an international center for one of the most complicated congenital heart lesions known to man. We have patients come from all over the world for our surgical and medical expertise for this heart lesion. And so this doesn't look anything like a heart to anybody, right? And in fairness, this was drawn by our senior surgeon about 10 minutes before he went into a 15-hour operation on a 3-month-old baby to create blood vessels that go out to the lungs to bring deoxygenated blood to the lungs to pick up oxygen. And so he drew this to explain to my partner at Lighthouse what it was that he was going to do. And so we took that to our engineers, our software engineers, and we got a little bit closer. Okay, so this starts to look like this is an aorta. That's the big blood vessel that goes into the heart. These are the blood vessels that our surgeon's going to take off and then sew. And we got to kind of schematize a little bit and gave it some color to show you which parts have oxygen and which do not. These are the blood vessels going out to the lungs. And we finally arrived at this, which was in 2013-14, which is an iPad application that is available on the Apple Store that our patients and families would download before they came to surgery from literally all over the world. They would come from Texas or Poland or wherever they were from, and they could actually do a schematic version of the surgery that their child was going to undergo. And so in the intensive care unit, when I would care for these families, they would keep saying to me, I did the app before surgery. It was so helpful to understand. Thank you for doing that. And so that was then. So that was in 2013. And I'm going to try here and take a moment and show you where we are now. So let's see if we can get this up and running. Okay. Headset's not responding. Let's see. I might need a moment here. Excuse this. So I'm going to put this on, and if I come out of virtual reality and nobody's out there in the audience, I'll know that I didn't get it right. Let's see. Well, I might need to pause that and try it another time. Well, this might not cooperate for us today. But let's see. We'll try one more time now. Okay. Well, what I'll do is I will try that again in a moment. But if that doesn't work, then I can go back and show actually a video of it. So essentially what we do in this is we're able to allow trainees and families to actually go inside the heart, to interact with it, to do schematics of surgeries in VR that gives them a 3D representation that they're really not able to get in any other way. And let's see if this will. Okay. As I do this here, what I'd like to show you. Okay, not going to cooperate. This is in comparison to how do we take care of patients when they come to my clinic. So this is when a patient came to me, and this is actually in the intensive care unit where I take care of these babies, right? So this is a 3-month-old baby. Mom told me that it was okay to use this picture. She's incredibly thankful. I met this baby when he was about an hour old with congenital heart disease. And this is the actual picture that I drew them in the clinic of what the baby's heart was and what procedures and surgeries we were going to need to do in order to allow this baby to survive. Really complicated and really difficult to understand, even for medical personnel. We have frequently these kids will show up in an emergency department, and it's almost impossible for the emergency physicians to understand, how is the blood going around and what is it that we do with these patients. So fast forward a number of years, this is that patient. He's now 6. And so this was a really kind of a touching moment. Yeah, we have a good team. We have a really good team. And so the mom and the patient, Rowan, they came to check out the virtual heart. And they were actually interacting with it. And this was for a story in the press that ended up going to the Boston Globe, which we were pretty proud of. It's my hometown newspaper. And what was interesting and really touching was that the mom actually brought the hand-drawn pictures that we had given her when her child was born. So 6 years old, right? And she keeps these pictures because it's just this really important representation of what her child's been through. And she put on the VR headset and got into our virtual heart and just said, this is just completely different. It's a completely different understanding and a completely different way of looking at the heart. So we thought that we were on the right track with patients. The other area that we've also used, as Walter mentioned, is with trainees, right? So we have trainees that come from all over the world to Stanford to learn, what it is that we do, to learn how to take care of these complex patients. We run a program called the Fellowship Bootcamp. You can see me up here where I had a beard that year, where we show trainees, with anatomical heart models. These are lamb hearts that I get from a local butcher. That we show them the anatomy and physiology. We're trying to get them from here, trainees, right? So this is me at the bedside of another patient. And going from here to here, it takes a lot of years and it takes a lot of training. And so and it's a very, very steep learning curve. And so we think actually that we can get these trainees further up that steep learning curve to really help them understand in 3 dimensions what it is that they're trying to learn. So it's also really important, one of the things we've done at Lighthouse and at Stanford, and as Walter mentioned with the research study at Project Braveheart, is to really make sure that while we are happy to use the kind of cool wow factor of VR in medicine as an entry point to kind of get people engaged, get people involved, I love it when people tell me, oh my gosh, if I'd had this in high school, maybe I would have gone into medical school. That's really great. But you have to actually prove that it's doing something. We have to prove that there's an educational, at least that it's not inferior. You can't be teaching people in VR unless there really is data to back you up. And so we took, with a relatively small study here at Stanford in the dean's office at the School of Medicine, 22 physician assistants, master's level students who were, importantly, median age was around 30. So not, 20-year-old or teenagers who were used to using VR. Most of them were VR naive. All of them had prior cardiac education. So they came in with anatomy, gross anatomy training already. And we put them through about a 7 to 10 minute VR experience with the Stanford Virtual Heart and found that actually we were really able, here's a couple of examples of the questions that we asked them. Anatomic questions such as what is the moderator band, what are the differences between the 2 ventricles, were some of the somewhat more complex questions. Some of the easier ones are, the pulmonary veins, where do they drain? And they did very well before and after. But this is what we found. Before VR, so already having had standard cardiac education, they got about 65% right on the 20-point quiz. After VR, they went up to about 90%. And when we analyze that statistically, it's very statistically significant. This is in the process of being published. This is important as well. So we asked them also, they could answer as many as they wanted. How would you prefer to learn? What is it that you would want to do? One of the things we're really sensitive to as well is people, especially in medicine, are appropriately enamored with the concept of cadavers because it's a transformative experience for people who go from being students or regular civilians to doctors. Like, you come out the other end of that, and that's a transformative experience in medicine. We're not looking to replace that. But when you ask learners, how is it that you would want to learn about the heart specifically? And I think for sure, as we go forward with more and more people using VR, with Mark Zuckerberg saying he's looking to get 1 billion people in VR in the near future, and with current millennials that are they're going to be just native to this. More and more people are actually saying that they prefer to learn this way compared to other methods. And I think as long as we can show at least that the learning that they're able to do is not inferior, and if they prefer the VR methods, that can be a pretty powerful statement for education. I think that's pretty important. One of the really cool aspects of being able to build this program is working with Stanford. We've been able to establish what we're calling the Stanford Virtual Heart Pilot Program. So we've connected with both educational programs and academic medical centers on every habitable continent, which means that not Antarctica yet. But we have groups everywhere that are using the Stanford Virtual Heart. We're going to be doing multi-center trials for education. It's really interesting when you talk to the people in Australia, right? They may not want to know as much. In fact, they didn't want to know quite as much about the most complex congenital heart diseases. They really wanted us to build them a model of rheumatic heart disease because we don't see that much in the States and in developed nations. But in other areas, and certainly in Sudan, they're going to have very different cardiac issues that they're going to want to represent with VR. So transitioning just briefly from healthcare into sciences in general. So Lighthouse, with a local company as well called Smart Sparrow, for the 2017 Department of Education EdSim Challenge, we were a finalist, one of 5 finalists, where we created a virtual reality representation of cell biology. And let's see, I can show you, I believe. See if we can run that. Yeah. So here, you're in VR, immersed in this environment where you can select to go into a neuron. You can learn about the nucleus. You can learn about ribosomes, or you can be in a bacterial cell and look at the cell wall. You can also be in a plant cell. You can learn plant biology. This is the part where when I first saw this, I said, oh my gosh, I got ripped off with all of the biology that I had to learn in college and medical school with this big book called The Cell that was so boring. We've created an in VR learning atmosphere that we're really excited about. Here we're going to make ATP from a mitochondrion here. So this, if you want to know the meaning of life, like that's it right there, ATP. And you're holding it in your hands. The learning profile that I showed you before is, you're kind of in VR, and we're able to create, tasks, representations of in VR learning that has really been both a challenge and really exciting to think about, well, how do you represent learning in VR? You can do things in VR like, for example, painting the path of blood flow inside of a heart that you just can't do in any other area. So there are whole parts of education and learning that we haven't even tapped into that are really exciting for the future. A couple other projects that we're working on as well at the Stanford Children's Hospital and also at the adult hospital as well is we're a fetal medicine and fetal surgery center where we do complex intrauterine and fetal surgeries. And so we're developing models of the brain. We're putting in what are called VP shunts, which drain fluid off the brain when too much fluid develops. And also in adults, right, the incidence of coronary artery disease is the #1 killer in adults and far more common than congenital heart disease. And so we're working with Stanford's heart failure team as well to develop the first in-VR educational and training module. And we've had a couple of fun moments just to share with you. So, it's always fun to have the kids in VR and kind of representations from our Stanford Children's Hospital. We were in the audience in October when Mark Zuckerberg said this and put our Stanford Virtual Heart up there and just about passed out when he said that because we thought that was a pretty cool moment. And not just cool, but actually we thought really true. That I think that there's the potential for this kind of technology to just completely change the way that we train and educate people. Let's see. I'm going to see if I can pull up, do I have a couple minutes, if I can try and pull this up as we're doing questions. But if it doesn't work, I also can pull up a representative video that will give you a little bit of a sense of what we're working with. But I'd be happy to answer questions. Thank you again for speaking. Sorry that the system timed out here, but such is life. Okay, can we actually change to this computer for a sec? Let's see if we can change to this one. And volume? Nah, it's all right. Thanks, though. So here what we're showing is you're taking this congenital heart disease here. You can, what we do is called explode the heart into its pieces. You can pick up the heart, and there we're showing you what's called a ventricular septal defect. I'll go back for a moment. So here's a heart with a hole in the heart. So this hole right here is not supposed to be there. Very frequently we have kids that are born with the hole in the heart. And so this representation shows you can actually go inside this heart. Here's the hole. You can close it so that you can see the difference between normal and abnormal. We can show you the physiology, the way the blood flow goes. You can do simplified surgeries where you're actually trying to understand what the surgeons are going to do in the operating room. And we really do think it's a better way to learn. It's just been really exciting to develop and to use with our patients and trainees. And so I'd be happy to talk more about it or to see if I can get this thing fired up so that people can try it as well. Yes?
My understanding is about 10% of us don't have real convergent vision.
Don't have?
Convergent vision.
Okay.
Right? So the occipital lobes aren't processing the information from two eyes. Most people are not even aware that this is a part of their being. And I wonder if you or Walter have given any thought to whether it's as a teaching tool, this may be less effective for those.
That's an interesting thought.
The kids when I was teaching histology who couldn't use a binocular microscope without getting a headache.
Interesting. We haven't had that specific problem with people using this. So I can say that, between conferences and, doing different demos and taking this kind of on the roadshow, if you will, we've had over 600 people use it, and I haven't run into that problem. So if it is about 10%, which that's an interesting number to know, I haven't come across that 10%. Everybody that's been able to use it appropriately and learn from it. The other question that kind of relates to that a little bit, which is important, and I think especially if there's any people considering developing VR in the audience, is the concept of motion sickness. And a lot of people get concerned about that. And I think that's important to acknowledge. And I think especially because we've actually been able to overcome that. Motion sickness you get because if you are in VR and you're actually floating through things, so in all of our VR experiences, you can teleport. So I can go from here straight to there, but I can't actually float. And people talk about the magic school bus and Mrs. Frizzle or whatever going, flying through the bloodstream. The reason that you don't do that is because if you're moving, your brain and your eyes are telling you that you're moving, but your body is not, and then you get sick. So out of those 600 people, we've had a number. Obviously, you say, "Oh, I get motion sickness," and nobody's been unable to do the VR experience. So I think it's certainly important to think about those learning differences or those differences in vision, but we just haven't experienced that. Walter, I don't know if you've had that experience as well.
I think with the mobile VR systems, you have that challenge where the high-end systems, more or less focus on it. But as David points out, it's a design issue. You can certainly design your system poorly and it will make it sick. But good design, you shouldn't experience motion sickness.
Can we? Yeah, all right. So actually, do I have a couple minutes where I could do this? Okay, great. I'm going to show you here. Not in the sequence I had intended, but okay, is everybody still there? If you walk out, then I'll know when I get out of this, right? So can you see what I'm seeing up here? Yeah. Okay, so this is our Stanford virtual heart. So you're kind of in this neat room. Over here, for anybody who's done any medical training, so this is Gray's Anatomy. So we put this up here kind of a little bit as an homage to the classic texts, which are beautifully represented, but they're obviously pretty flat as well. Over here are the three-dimensional plastic models that we use as well. And on the table there is Stanford Medicine Magazine. And that's just to kind of show, where we've been, a little bit of fun. And so, we have a number of heart lesions here that we can select from to kind of show either patients what heart defect they have so they can understand their heart lesion, or also we can show trainees to help them understand how to care for these heart lesions. I'll take this one off here, and as we're doing this, I'll kind of teach you a little bit about congenital heart disease. So I selected ventricular septal defect, which is a hole in the heart. And so as you look here, one of the things we constantly have to teach people in congenital heart disease are the structural relationships of different parts of the heart. And so, for example, if you look, this right pulmonary artery right here, almost always in the normal heart, goes right underneath the aorta. That's just anatomy and how it does that. But to get that physical picture of how it is in 3 dimensions is really challenging. And while you're looking up there on a flat screen, I mean, this is completely 3-dimensional for me, and so it's a little bit of a different environment when you really get inside. You can expand the heart to kind of explode it into its pieces, right? And I can still look at the different parts. I can pick up heart pieces. So here's the right ventricle. This is the left ventricle. Here's the right ventricle. And now I'm going to show you, so that's the hole right there. And so that's not supposed to be there. So these are valves. This is a tricuspid valve and a pulmonary valve, if you remember from your biology. So you can actually see how the valves are moving. I can kind of scan in and out. There's the pulmonary valve. But this hole, that's not supposed to be there. And so that can really create a big problem for the patients. So I can look all around here. When I'm ready, then I can go inside. And so this is where you kind of get that VR wow factor, which is fun and neat, but it's also important to use for, okay, good. You can also use that to teach people, right? And so look, we've put different labels to show what different things are. Hopefully you can see there. There's blue. Snooze that. That's Stanford telling me that I'm not in compliance with something, as always. Oh, it's getting recorded too, so my boss can see it. So we can see here that these are red blood cells. The blue ones show that they don't have oxygen because they're coming back from the veins. But these red ones that are coming through this hole have already picked up oxygen, and then they're going back to the lungs. So that's an inefficient pump. That's not what you want to have happen. So let's go over into the left ventricle. Now we're in the left ventricle. So here's where blood is coming from the left atrium with oxygen, and then it's actually going back through that hole through the ventricular septal defect, and also out the aorta. So that's what we're trying to teach people. And then let's see if I can get this to be able to allow us to do the next step. It might not. Okay. And so the next step after that as well is when we can actually do a relatively simplified surgery, which is similar to the one that you saw there. I think the sensors got confused after I moved everything around. Okay. So that's the first congenital heart defect. We have, right now we're in the process of building much more complicated congenital heart defects as well, but I can show you just briefly, others. So this is one called coarctation of the aorta. So the aorta being the big blood vessel that comes out of the heart. And you can see here, this one has a narrowing, which will not allow blood flow to come out through the heart and can create significant problems for babies immediately after they're born when they need to have surgery. So that's kind of just a quick tour of our work, and I'd be happy to give you more references so that you can take a look at it, or even if people are around to take a quick look as well.
And we're about to have a break, so.
Great. Thank you.